Welcome everyone, and thank you so much for joining us today for the Grasp on Robotics series. Just as quick reminders, this and previously recorded talks can be found in our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Now, without further ado, I would like to introduce our Grasp faculty host for today's talk, Dr. Cynthia Sung, Gable Family Term Assistant Professor at the Mechanical Engineering and Applied Mathematics Department within the School of Engineering at the University of Pennsylvania. Thank you.
Great, thanks, Gabby. Hi, everyone. I'm so excited that we can welcome Professor Sangbae Kim today for our GRASP seminar. Professor Kim is a professor of mechanical engineering at MIT and the director of the Biomimetics Robotics Laboratory. He does a lot of really interesting work in bio-inspired robot design. You may know him from his Cheetah platform, which is world famous and very, very cool. He's received a lot of different awards, including multiple paper awards, a DARPA Young Faculty Award, an NSF Career, and many other distinctions. I'm excited to welcome him here today to talk about robotics with physical intelligence. So thank you, Sangbae, for joining us today. And we're excited to hear what you have to say.
Thank you, Cynthia. Thank you for inviting me to be in this webinar. I'm happy to see you. I'm again, like it's not normal. So I wish I can see you guys' face, but I wish you guys enjoy the talk anyway. So I will share my screen. The video will be a little bit choppy, but I hope you understand that. It's kind of strange, even in this like heavily developed IT world, we still have a bandwidth issue. My talk will be robots with a physical intelligence. This, I'm going to just typically, like most professors, just give a talk, what's going on in the lab. This time, I'm trying to have a little bit of direction. I want you to kind of take this opportunity to think about things we might not really notice usually. The word, the physical intelligence might be very new to you or like strange to you, which is very normal because I just made up. And the term is something I just found at my best. I had a trouble finding right word because something we don't actually have a languages. And one of the reasons why we don't have languages because we do it so seamlessly, subconsciously, like using your hand and grasp things and moving around, balancing, a lot of body movements. You don't actually use language to communicate to your siblings or your sons or your parents. This is something we don't have enough languages. So I hope you have a better understanding what I mean by physical intelligence, and hope all of us get together to build these languages or abstract concept to really move forward our robotics. So let me start. Because of pandemic, I think IT services are even more, developed and getting more attention. I'm not necessarily sure there are new technologies coming in, but I think the usage and then the commercial value goes up. Because everybody wants to stay at home, but everybody will notice that even in this pandemic world, physical service is actually very, very critical. Like you can't just you rely on IT service to like create a food and deliver food. There are still a physical service has to happen. You can think about many things: delivery, home security, smart factories, and farming, construction, and disaster response. Especially elderly care, all these things, you can't just have a web software to solve these problems. These services has to involve like physical work and energy and force and dexterity, skill set, and so on. So we already start seeing this offline and merging with the online services to make a new business and looking at the future, because IT services will be as soon as it's going to be saturated. There's going to be always new services, but it's not going to be completely new technology, because what we can do through the bits and the internet connection is limiting. It's only about information. You can't really deliver a physical energy through the internet. This is, let me quickly optimize. Oh, optimize already on. This is a factory of BMW. Let me go back. This is a basically physical service we have now as a robotics perspective. These robots are very capable. They can make robots. They make their cars and sometimes make robots much better than human. They're much more precise. They are much more reliable. They just do the same thing over again, and then without mistake. They're faster, they're stronger, they're fantastic. But one thing you might notice that they are not quite making a rich contact with the object. What do you mean by that? Whenever you need like a task that need a rich contact, like manipulating soft object, humans are there. In this like a massively automated factory, there are still humans are involved to do something very simple things, and there are looks like that could be replaced by a robot. That actually is not, because these involve very soft, delicate object that you cannot just finish the task with just a position controlled machines like the other part of the factory. And these robots are very capable, but there's no actual intelligence. These are just repeating same pattern motion again and again, and the very minimal even feedback. There are some of them has a force feedback, for example, welding, and a few examples, but most robots are pretty much repeating motion again and again to finish their job. So these engineers are actually very good at making manufacturing tasks into position tracking problem and then solved, because then you don't need to worry about feedback, we don't need to worry about stability and so on. So we've been doing this for like last 50 years. But when it comes to the actual physical service in the street or in your home, this is not going to work. So you have to really think about it. These robots are not going to be good when it comes to mobile case. You know, you're seeing the contrast between the DARPA Robotics Challenge to animals, because those you start seeing the contrast from previous slide where these agent, these animals or robot has to be outside the factory and that cannot be anchored on the ground, which means you have to move around. As soon as you start moving around, you lose the capability of just finishing everything in the position control. You have to balance first. And then when it comes to any task outside the factory, your task is not necessarily easily encoded by position trajectory. If you think about your just try to grasp anything in your table, and then think about how your hand is grasping, and then try over again, and how important the position accuracy is. It's not so much actually. Your hands are constantly colliding with things. You have to have a higher level intelligence, like when your finger first, the index finger hits something or middle finger hits something, your action is different. It's not necessarily predefined trajectory you already have in your brain and executing it. You're way more reactive, and then position accuracy is much less important. Your reactive force controls are way more important. And collision is happening all the time. As soon as you walk out of your room right now and then grab your door handle, you realize your hand is actually colliding with your door handle constantly. You just don't realize because it's happening in the subconsciously. So I've been thinking about this problem for last 15 years and trying to make a paradigm shift from this grounded, structured environment where precision position control solve most problems to the environment where things are very unstructured, and then positions are not always known. You have to balance yourself because robots are not anchored and grounded, and you have to interact with the many things very fast, including collisions. So before thinking about intelligence, I actually worked on the hardware, how to do this. So I'll quickly show you some of my previous robots that kind of fall into the same categories, because these robots are all mobile robots. So I had to have a like specialized machine. This is an Ice Pro, the first robot I built, and this is a cockroach-inspired running robot. At that time, it was like fastest running robot per body length. Now, Ron Fearing and Berkeley actually have a better record. This is, you might notice, this is a sticky bot. This is a world first directional, synthetic directional adhesive. So robot is cute, but the pad on the robot is really, really cool. This is probably my favorite scientific research I ever have done. We invent a new type of material that didn't exist before. So these adhesives are actually sticking only one direction and then doesn't stick in the other direction. That's exactly how actual geckos are climbing up and then running up the wall almost as fast as running on the flat ground. The third one is probably the strangest robot I ever built. It's about 1 gram weight. So if you blow air, it will just roll. But has a very interesting structure. It has a no rigid component inside. It's pretty much all fiber, including muscles. So using peristalsis. It's a peristalsis sequential contraction motion happening in a worm and this invertebrate animal, or in your intestine. And your intestine actually move things inside your food using peristalsis. That was a very interesting soft robot I built in 2009, 10. And I was involved in many different Bi-Inspired robotics, but I really want to make robot that can actually do some work. So I jumped into the MIT Cheetah design since 2008. And this is the video of Cheetah 1. This is the first time we barely make it walk on a treadmill with the constraint. So couldn't balance in 3D, it was only balancing in 2D. But the energetics was quite remarkable. At the time, which reached 0.4, 5.5 cost of transport. For that weight, 0.5 is equivalent to the animal level. So that was the first Cheetah one. I will show you the rest of the Cheetah in one slide. So I'll show you Cheetah 2 first. I'll kill the sound. Cheetah 2 this is the fastest robot we ever built, and then this is actually finally balancing in 3D. Maximum speed was a 30 mile per hour, 60 meters per second, which is probably like faster side of me jogging around. Quite my sprinting, definitely much slower than real Cheetah, but it was quite exciting. At that time, there's no electric machine could do this. And also autonomously jumping over obstacle using LiDAR sensor, and then autonomously adjust a step and then optimize the jumping trajectory in real time, because we finished optimization 100 milliseconds. So we solve like 10 times in a second and then use the last one. And this is Cheetah 3. We move on to much more practical shape rather than like dynamic and fast running robot, because Cheetah 2 was fantastic, but it couldn't turn very well. It cannot walk sideways. Cheetah 3 is a lot more omnidirectional machine. You can walk sideways, spinning, walking, anything works. And also we start using and much more rigorous model predictive control. This climbing is also kind of interesting. If you look at it, there's no vision. We wanted to maximize our blind locomotion capability before adding visions, because you can't really rely on all the accuracies of vision, because there's always going to be state estimation errors and vision blur and occlusion and so on. And Cheetah 3 was great, but Cheetah 3 is like 45 kilograms. It's a very heavy and dangerous machine. So we actually start building smaller robot to actually work with other groups as well. So this is, you might not see the speed. This robot actually was running about 4 meters per second with that size, which is remarkable given that this robot is only 60% of the size of the Cheetah 2. And the cost is actually very low. So we actually built many of them. I'll show you the picture. We try many different gates. And because this robot is so small and the light, the ease of experiment just skyrocketed. So compared to Cheetah 3 or 2, our emotional score on like how easy to do experiment, it's like 1,000 times more. So my student, we need to like call a day or time and at least recruit 3 people to have one experiment. Now these students are doing experiment by themselves on the desktop. This is probably the most advanced controller we built. It's called the RPC, Regularized Predictive Control. I'll explain that a little bit later after this video. This is a remarkable performance, but I will tell you what is actually special about. You can turn, I remember, 2 radians per second. And all the little detail behavior is built in. Thanks to this safe robot, one of my postdocs actually brought one mini cheetah during pandemic and then continued to experiment until he realized it's bothering his neighbor too much. And then he has to buy a couple more yoga mat, and then robots are not so happy because the yoga mats are too soft. And he eventually gave up, but at the time we opened our lab, so he was able to experiment in the lab. So again, the blind performance is very important because you're not looking at every single step. You're not going to have a camera everywhere. There's going to be something occluded. There's going to be unmodeled friction there. You can't really predict everything, and then you're never going to have an optimal trajectory anyway. So this is the first time we had a camera, pretty rudimentary algorithms, but we're still working on it. So camera tell us high slope and low slope, like vertical surfaces are not good place to put the foot down. So it distinguishes good place to make a foothold and a bad place to foothold. So it distinguishes, and then if the place is too high, we'll decide to jump. So these are reasonably simple obstacle, but it still make a huge difference now once you have a vision. So we're continue to improve our vision cameras and then better sensors so that we can actually eventually handle much more rugged, much more difficult environment. I'll quickly explain what RPC was the most, I guess, unique control. We have many different controls in our lab, but I'm not going to talk about the details, especially in this short period of time, but I'll tell you something to remember. Roughly, our controller path planning is coming from human input or the vision system. Vision system says, don't go there, go straight here, turn left. We have a trajectory planning algorithm as well, given the obstacle. They will give a body trajectory, and the model predictive control using very simple model, one rigid body model, to optimize the torque input of each joint, looking at next half second in the future. Don't ask me why is half second. We just picked that number. We thought it's given the bandwidth of the robot, 0.5 seconds is roughly the horizon we need to take a look. And also that's about one half of cycle, so have one step of the robot. And the motor predictive control basically give out optimal torque profile and then give us suggested body trajectory. And whole body dynamics basically take care of everything and then try to make sure that happening in full dynamics, because MPC cannot run on full dynamics. That's way too much, too big a model to use on this fast optimization routines. So whole body dynamics is not looking at the future, just get what MPC tell us, and then just execute in time. So it's running much faster, 500 hertz, where MPC is running, given the situation, like 40 hertz to about 100 hertz. The issue is your cost function. Whole body dynamics, we don't have a much problem, but MPC, what is your cost function? This is not just our locomotion problem. Anybody's working on any algorithm in robotics, you probably face this problem. And then you might not tell everything to your advisor. Your advisor probably hear only a gist, but if you're a grad student, you probably know the agony of tuning cost function. Cost function, and then you don't talk about cost function in your paper. That's another problem. Because there's no science on how to tune the cost function, but the cost function is everything. If you don't put the right cost function, none of our algorithms work. And thankfully, locomotion is a relatively simple task. You're just walking around on the ground. Well, ground can be quite complex, but if you know where the body you want to go, and the cost function can be written reasonably easy, because minimize the difference between what I want, where I want to go, to where it is. But even that simple task, cost function tuning is not easy. Our initial cost function is obviously minimizing the square of minimizing the x position, y position, and velocities, and so on. Turns out that that's not enough. The reason why is trying to follow the trajectory with our weight doesn't necessarily guarantee stability or versatility or agility of the robot. There's no translation. If you really think about the agility and then stability, I'm not talking about stability in the rigorous control theory sense. Here, stability is like very abstract concept in very complex dynamics. Like, oh, that looks more stable. It's all human factor. Like only human can judge, or that you can do it. A few primary, for example, maximum speed, maximum turning rate. There's a few quantifiable number we can verify. But that's also after you run all the optimization. You cannot plug that in before running optimization. So my student actually come up with a regularized predictive control. So there are many things going on, but only thing take a look at is a heuristic model. He called it heuristic model, but actually this is not just human intuition. He actually used the data once you run optimization based on your cost function, and then look at the data. And then, oh, this is not proper. And then you bring back the data into the cost function and then tune the cost function to be more a proper way to go. Sometimes when you go straight, your pitch is down for some reason. There's a model difference between your model to the reality, and something you don't like about, because even though you're trying to minimize certain value, your weights are off sometimes. Like you're comparing radians per second to meter per second. And how are you going to decide the weight on this? And depending on moment of inertia to weight kilogram, the units are all over the place. There's no way to unify which one is more important to chase. And he actually add a non-conventional cost function based on the data. So this heuristic model actually is keep on evolving through the experiment, and then having some strange cost function start showing up. And that eventually cycle allow us to have a much better cost function to run our robot very robustly. And can we do that in some sort of machine learning fashion or other optimization? There are people trying to do that, but again, I think eventually what we want from robot, where robot is not just running straight and wants certain speed, or we want the robot to turn and running going straight and turn, and you want to stop quickly and then turn, or jump, and like things you want to happen. It's just so many, and then there's no one good metric that represent the best performance of those. I mean that one metric eventually is your optimized cost function. But at this point, some sort of systemized feedback from the data, and then there's some human factor comes in, because you cannot really quite automate this, because some weird metric, another cost function, you need to create another cost function to turn the proper cost function to maximize your performance. And if your goal is just going straight fast, and that's probably possible, but if you want to do many different things, and that's going to be very difficult. This kind of problem is not only happening in locomotion, it's happening in everywhere. I can give you one example: safe driving. You cannot easily write a cost function to make sure that will guarantee, if you maximize this, your driving is going to be safe. That's not possible, because it is human factor. It's appear to be safe is also very important. Literally safe in physical sense, and some quantifiable sense, is not going to work with the human. Because even though the driving is very safe, if you appear to be dangerous people, you have to change it. Let's talk about actuator, because that's probably the more important thing in our this talk. This proprioceptive actuation we started promoting in 2009, 2008. Again, this is not completely new. The Ken Salisbury and the Phantom, the haptic community has been using, getting benefit of this idea. Unfortunately, there's not many papers or written article about why they designed this way and why it's so effective. And then 2008, I realized this is a way to go for every robot. It's not just for haptic device. And then we start writing why it is and how it is. And it is about how you actually design your limbs differently. Somebody asked, what is so special about it? Special about it, it's actually that this is a very good example of a less is more. What is so special about it is actually it doesn't have enough sensors. It doesn't have too many complex parts. It actually focuses on inertia distribution of the design and then get rid of force sensor feedback at the end. I'll explain that more. So if your robot is not like a factory robot, like very slowly approaching the object, that's gonna take forever. If you look at the Amazon picking challenge, the things that takes the longest time is actually approaching object very carefully so that you don't throw the object or you break something. But that's not how human works. If you just play with your hand and your object right in front of your desk right now, you'll soon realize your fingers are constantly colliding at high speed. So when it comes to collision or high acceleration, this is basically what happened. If you think about a body and then limb and then the ground, this is a leg robot example, but you can actually flip the side. You can think about it as a manipulator as well. Your manipulator is anchored on the ground, but your limb is approaching something and then hit something. And in a high acceleration case, what you command, like body say, apply 10 Newton, is not going to be same as what's actually happening at the ground because it's high acceleration. And then in high acceleration case, inertial force dominate. What I mean by inertial force, things that start moving down and then as soon as it hit the ground, you have to decelerate quickly. And then that kind of force is caused by this kinetic energy of this inertia. And what are those inertia? Not just these limbs, that actually rotor inertia is actually much, much more important. Gears, frictions, and so on. It's all lumped here. This is real data on your right. This is an actual cheetah running, bounding on the ground. As you can see, the robot command the blue. I command very little force, but real force came out much, much higher. That's not something we control. This just happened because of the impact, because of the high inertia of the limb, that connecting body to the ground. And that acceleration times the mass caused this uncontrollable impact force. So as you can see, if I want to control ground action force very well, which is blue and red, I want to minimize difference between blue and red and high-speed collision, your yellow should be very small. In order to minimize the yellow, you either move very, very slow. That's what's happening in industrial robots or any other robots currently, or make inertia very, very small, make the mass very, very small. So I can move reasonably fast. That's basically the idea of the proprioceptive actuation. There's a terminology people use on backdrivability, which is actually not a very good term. It's not very well defined. So we actually define our own term. Eventually mass is, inertia is actually most important factor here. Damping, not so much. You shouldn't have too much damping and shouldn't have an impact. If you have too much damping in your system, that's bad design. And there's another thing I want to point out here is a friction. There are many different types of friction. Here I'm talking about friction through the gear train or transmission, where the friction is actually proportional to the force input or contact force input. Those appear as inertia as well, because it's force-dependent friction. If you increase the force, it reacts against you, impede more proportional to your force, which is basically inertia. People don't realize that originally. So if you have a small rotor inertia, for example, but if you have a high friction in the gear train, which appear to be very high inertia. So in order to talk about rotor inertia, I changed the design a little bit, changed the diagram a little bit. Still same body. This is the basically limb. Most people look at the limb inertia only. The limb inertia is actually negligible, very, very small. I shouldn't say negligible, but much, much smaller. Eventually, rotor inertia is dominating. Well, rotors are very small, Sangbae. What are you talking about? Including the gear train, the gear ratio basically amplify the gear inertia like dramatically. So if you think about MIT Cheetah case, the proprioceptive actuation, our case, the ratio between rotor inertia to the limb inertia is actually 50-50. If you grab like industrial robot or Honda Ashimo, this ratio become 1:99. The rotor inertia is 1, the limb inertia is 1, rotor inertia is like 90%. That's basically most of the robot in the world is the case. So people, but yet, if you look at most dynamic simulation, including bullets and many other commercially available high quality dynamic simulation, they don't include the rotor inertia, which means when you use those dynamic simulation and collide anything, your force is completely bogus. Your robots are not doing exactly the same thing as your real robot would do. So please keep in mind if you're doing any research and anything like reasonably fast, you have to have inertia. And it's not trivial, actually, rotor inertia inclusion. You have to play with your mass matrix manipulate, or if you, especially most of this dynamic simulation use articulated body algorithm, Featherstone algorithm, adding rotor inertia can be very, very tricky. Again, backdrawability is not a right term. Impact mitigation factor is the right term. It's a normalized inertia quantity, which I will explain in next slide. So I'm not going to go through this old dynamic equation because you might not familiar with, but there's a concept of operation space mass matrix. What do I mean by operation space mass matrix? If you think about a single rigid body is a mass, you have a mass and rotational inertia. But if you have a robot case, like multiple inertias are combined, the mass matrix is a relative. Are you talking about from the joint space or the operation space? So what do you mean by operation space? Operation space is in the Cheetah case, the foot space. That's what matters. That's what it interacts with the environment. If a manipulation case is just the gripper. So if you close your eyes and then touch the gripper and then push around the gripper, and then you're gonna feel some virtual inertia. Well, it's not virtual inertia, real inertia, but effective inertia. That's actually exactly represented by operation space mass matrix. That's exactly what matters. You know, we're not hitting the body of the robot. You always interact with the end effector. So what you feel in terms of the inertia in the end effector, that's what matters. But the problem is, I want to know how backdrop, how easily this machine is designed to handle impact. And then that inertia is the most important factor, as I said, because in a high speed, the inertia dominate. But I have a robot, 10 kilogram robot. My friend has a 100 kilogram robot. And everything is different. You cannot really compare apple to apple. So we basically come up with a normalizing way to look at the quantify the inertia. So the counterpart is actually worst case. Worst case scenario inertia of this robot is basically the body coordinate inertia matrix, which means we're comparing with the worst case scenario when every joints are locked. So there's no inertia, the rotor inertia, there's no gearbox, just like hot super glue every joint and then drop the robot. And then your foot is gonna feel the entire body inertia. In reality, in the real case, it's actually not that bad because the joints are accelerating, decelerating, and then joints are absorbing some energy. So it's a real case will be much less, the operation space inertia will be much less than the worst case scenario, every joints are super glued. So there's a relative inertia, which is the basically IMF term, determinant of the, the comparison between the identity minus this locked case to the normal case. This is one way to quantify how easily, your robot can interact with the environment. Our Cheetah case is 0.9. Some of the high gear ratio robots are 0.5 and so on. But that's very lumped representation. One number cannot represent the robot's inertia because the inertia has a 6th dimension. So you can actually tease out, instead of doing determinant, you can actually look at the X direction, Y direction, Z direction. You can take a look at those numbers and make in the vectors, whatever you want, because inertia matrix is not, inertia in the X, Y, Z is going to be all different. So let's stop using backdrawability. I think IMF is a properly quantifiable metric, represent how easily it can interact, handle the impact, and then observe energy. This is a Cheetah running on the force plate. So robot is commanding some force profile and then just running over a force plate, and so we're trying to compare the what we command and then what's actually received. Again, the impact force we can't really control. And there's a lot of dynamics going on, and because we don't have a force sensor feedback, but we're roughly matching what we commanded, you might think, oh, that's not very good. But I want you to have a perspective. This is an 80 millisecond. That's all you have. In the 80 millisecond, your blinking of eyes takes about 300 millisecond or so. So 80 millisecond is an accident in most robotic experiment. But we actually have to control the ground direction force during 80 millisecond to 100 millisecond. That's a typical ground time. And the why has to be so short. Oh, well, that's actually how it is. If you human, much bigger animal, running around, jogging around, your ground time is going to be 150 millisecond or 200 millisecond. When you grasp something, if I grasp something around me, your contact time is going to be even less than that. It's much, much faster. So if you don't have a proper high bandwidth force control system, you cannot do anything during the 80 millisecond. If your force bandwidth of your system is like 2 hertz or 5 hertz, 80 millisecond, you have a zero control over that short period of time. That's why we had to design our robot a very special way, which is proprioceptive actuation. In Cheetah 2-3 case, we actually need to design our motor from the beginning. We design our controller and so on. And every small piece of design is actually optimized to maximize force bandwidth, which is actually same direction of maximizing IMF. This is not irony, it's actually same physics we're talking about. Speaking of actuator, I want to just quickly go through what type of actuators we have. There are way more, but I pick out only a few. Because what is really different then? Like, the typical manufacturing robotic arm is actually very, very highly geared. So gear ratios are 300 to 1, 200 to 1, because the payload is very critical in the factory. And then intelligence. I talked about physical intelligence, like the contact, force, how to handle impact, observe energy. Those are not in their concern. It was actually in the first programmable arm designed by Victor Scheinman. He was actually a mentor when I was at Stanford. Sadly, he passed away in 2016. But his first arm was actually designed to interact and do the force control, and he actually intentionally designed that. When it comes to commercialization through the Puma and then all these modern robotic arm, that concept just threw out the window, because position control, rigid, accurate execution, position execution is actually the effective way to do it in controlled environments. So true, I think there are people trying to make that barrier, but still pretty hard in the controlled environment, because there's always a way to achieve that with the position control only. People take a look how to minimize inertia so it can exploit that. Direct drive arm was very popular, but again, direct drive arm still very, very impressive. They do things like incredible speed, but direct drive arms are not used to make a contact. As you can see, the vertical direction is making contact. Those are all suction cup, because we still have a problem in inertia and contact. And typical direct drive arm doesn't have enough torque density. That's actually the problem. So direct drive arm never used to actually interact until recently. This is a company, Genesis Live Drives product. They actually designed a fantastic direct drive arm very recently to properly interact with the environment. They have such a high bandwidth system, so you can actually safely interact with the human finger. You can even touch the egg, doesn't break. All that is great. So finally, people take a look at this high force bandwidth and proprioceptive actuation is the way to go. One caveat of the direct drive arm, as I said, is it doesn't have enough torque density, so your payload is going to suffer a lot. But sometimes with low payload case, it can be very, very useful. Series elastic is one of the popular idea. Well, why don't we let the spring handle impact? You can mask all the inertia away during the impact. The impact location doesn't see the inertia. Good idea, but it suffers from complexity of the system and the bandwidth. You lose control bandwidth significantly because you're slow down the dynamics between the motor to the ground. So this body plot actually shows that the blue light is frequency. It drops significantly when the spring stiffness is not high enough. So all these robots eventually have a very, very high stiffness spring. And then now your impact mitigation is suffering. So I think it's some successful examples, but there's some trade-off. Series elastics are way more complex. And then you always have a suffer from the limit of the spring and so on. Hydraulics is the best actuator for impact. Not necessarily minimizing impact. It's just it doesn't break against impact, because that's why all these construction machines are designed. Because when a high force, all these forces are transmitted through the liquid. So it's not like one component takes a lot of forces. The liquid distribute all this stress, and it's fantastic technology. And BDI abuse it quite a bit a long time, and IIT and there's some Chinese company and Korean army use it. Hydraulic, that's a all-day story, and they realize the efficiency is terrible. So we believe that electric is the way to go. And that this chart might convince you that what I'm saying is true. The Ashimo was such a standalone example at the time. There's nothing else even close. But still using conventional hydraulic harmonic drive and very high gear ratio, like a manufacturing robot type of technology. It ran and walked and so on. It handled impact very differently. They have a very precise position control. It doesn't really work on any environment. You have to be very controlled environment. And ever since that, hydraulic basically dominate 2006 to like 2013. Boston Dynamics that show many fantastic examples of hydraulic machines. And then many other countries realize, hydraulic is the way to go. In the middle of that, we started doing electric robot, which is a Cheetah 1, Cheetah 2, Cheetah 3. And a lot of people send us a skeptical note, like, hydraulic is the way to go while you're working on electric. It turns out that electric robot can be very, very dynamic and then very, very robust if you design properly. And if you look at 2020, there's only one hydraulic, which is Atlas, Boston Dynamics robot. This is very challenging to achieve in electric robot anyway. There's too many degree of freedom. But when it comes to roughly 20 less degree of freedom or less, almost every machines are adapting our proprioceptive actuation, including Digit, including Coastal Robotics. These are all basically following our paradigm. Digit, and the Cassie, they claim to have a spring. Those springs are actually not quite a spring if you actually know detail. And controls are all pretty much the same way how we do. There's no force control feedback. That's a terrible idea. If you have any question, I can explain why it's terrible idea. It's quite complex, but it's eventually stability issue. Force sensor feedback at the end effector, you can achieve high bandwidth. So in 2020, I can't even count the number of companies actually copying our design and our control paradigm. And then many of them actually use our software. We actually have a open source software they can use. Before moving on to other topic, I will show you some of the new result, unpublished result. We're doing some serious trajectory optimization to create many motion primitives, like running jump, jumping whatever direction, like bounding jump. We're stitching many different optimization results to create many different type of behavior, a lot of ballistic behavior as well, to eventually visions data comes in. If you know where you are, we're gonna plan a trajectory, including jumping and turning and many different gates. We have to put together all this together in the high level optimization scheme. So we need to build a lot of these motion primitive doing local trajectory optimization. So these are optimizations are all offline optimization, and then we need to have them as a like arsenal. So you can, if you see that situation, I need to stitch this behavior to overcome this obstacle, for example. So if we start mixing jumping and spin, because sometimes you have to spin, jumping down and spinning. Our landing is still pretty primitive. It's just impedance control landing. Hopefully we can have a little more better landing controller. This is the standing spinning. And now it's just sided flipping. We call the barrel roll. which is kind of like equivalent to the backflip, but it's a sideways. So you can actually do, if you think about combining all this, you can actually climb stairs and jump to the, you can think about it like a real parkour, like a quadrupedal parkour, and the many very complex terrain. Of course, your upper level optimization should be very, very good. This is probably the, yeah, continuous spin, probably same thing you saw before. So we'll move on to next. This is already old story, 2008. We built the 10-minute cheetahs. 10-minute cheetah doesn't sound like a lot, but which means we had to build 150 actuators, all in-house. So 2-3 grad students sit down and using 2 tables. We don't have a factory space. 2 tables, we pile up everything, build everything. And then now mini cheetahs are in the U of Michigan, Notre Dame, IHMC, Berkeley, CSAIL, Naval Labs. Naval Labs is a company who sponsor us. And then they are all sharing this hardware, and they're working on their own stuff using our mini cheetah. We have our open source software. If you want, you can just search in GitHub, you can find it. We actually quite updated a recent version. If you want to see our recent version, just contact us. You can feel free to share so other people can use this more realistic dynamics environment, you know, including all this road inertia. We did everything properly. And we have now we actually have a better visual plugin. We started using Unity. So our software is getting better and better. So if anybody interested in using our software package, feel free to contact us. We plan to have this like a grand mini cheetah workshop where, you know, large venue or 10 mini cheetahs are playing each other, all that. Pandemic, no. So the IROS mini cheetah workshop is going to happen Zoom. Actually, next Friday, 9 to 11. All the speakers' talk is going to be recorded, so it's only having 2-3 hours to really talk about how to collaborate effectively using same hardware and same software package. Not necessarily same software, but, you know, basically how do we work together. So if anybody's interested, just let me know. I can send you the link. You can participate. It's a relatively small workshop, but hopefully we can make some progress in collaborative research in this direction. So time is running, but I will show you some of the new topic. We've been working on teleoperation for a while. This could be very critical for this pandemic situation. But this is, again, we're exploiting our proprioceptive actuation technology. There's no force sensor feedback, but this is probably, I'm not sure when you can try this, but this is the best teleoperation force feedback system in the world at this point. So stiffest and then stable, most stable. You can feel all the forces in the other side, and you can see you're basically between object to your hand, there's 2 sets of arms inertia you have to handle. So when you shake around, you're feeling the double inertia arm. So how important, very, very important to have a minimal inertia, and also very, very important to have a little inertia to feel the force properly. Any high acceleration, those inertia times acceleration will, you know, shield, like will bias your force you're feeling. We are also making our own force sensor. We're not thinking about using force sensor feedback to control the force, but this force sensor is designed for highly dynamic situation. Most force sensors are not suited for example, this ATI sensor. If you use this in highly dynamic situation, you will know how bad it is. It's not that sensor is bad. Sensor will pick up all this inertia as a force. But our force sensor actually is free from inertia. That's why we designed that way. And then these sensors are actually not only measuring force, also measuring the location. So you can measure X, Y, Z. At this point, you're showing as a tangential force, but also showing theta pi. So have a 2 angle, the contact location. So we can call that as a force sensor is more like contact sensor or something. And I'll show you one other demonstration. I'm not sure how fast you can see this. This is also, we have a lot of fast video Next time I'll slow down like factor of 5 so everybody can see it. This I call that as a virtual magnet demo. Obviously, the wood and rubber are not attracting each other, but I asked this. I showed this video to many people, and what do you think? What kind of algorithm running? And then people are very, very confused. This algorithm is a one-line algorithm. If you look at the code, there's one line is achieving this virtual magnet demo. So only possible with this type of low bandwidth, high bandwidth proprioceptive actuation with a very robust contact sensor with the force sensing capability. The line is this: just push toward the contact location. That's it. Even writing in one line, and then it does this kind of behavior. And this could be an example of what I mean by physical intelligence. When you touch something, you need to know what to do. Of course, this is a very small piece of it. We need to have many, many more pieces to actually achieve what you want. I don't know how to describe this in word. In the beginning, if you remember, like the physical intelligence is such a, you know, the very abstractly defined term. We need a better language. We need to define new languages to describe this very heavily rich context situations. And then we can talk about it. We can talk about writing paper. We need to decide what to say. People are start realizing the low inertia is very, very important. So Matt Mason's group, CMU, developed this direct driver finger, so we can actually interact very quickly. For example, when you pick up stuff from the ground, you don't need to wait for trajectory optimization to carefully approaching. You just hit the ground and then pick up, because proprioception allow you to sense everything. There's no force sensor here, same as ours. And Yongjae Kim is Korea Tech. He designed this unbelievably complex light arm. This whole arm is like 1.8 kilogram and 15 degree freedom. And they're reasonably impact free. It's not direct drive, but has a amazingly complex, but yet it's not like a sculpture like other typical robotic arm finger. And it can actually generate quite a bit of force and some precision. So again, all these people are start realizing the impact mitigation and then low inertia, high bandwidth issue. I want to show you one video, which is me picking an apple in blind fashion. I'm not looking at the apple, but I'm just thinking about grabbing one apple. See what happened. It doesn't matter if you cannot see anything, because we're not going to see anything anyway. They're very fast. I don't know what's going on. You only can realize what's going on when you're moving very, very slow. You're actually colliding your finger constantly, and then try to grasp something. I don't know, I just paused the video. If you think about, if you write a control algorithm, if your robotic finger have sensor and then touch something, you probably run some algorithm to optimize, okay, find the easiest apple to pick, some metric, and then probably will pick one of those two, right? Turns out that my hands are much more dumber. It's not quite intelligent. It's not picking that. It's just trying to grasp right there, and then ended up touching 4 or 5 apple, and ended up choosing something the hardest. I don't know what kind of cost function I'm running in my hand, but I don't know. This is happening subconsciously. And then obviously there's a lot of apples on top, so it's not easy to pick out. So I want to secure the grasp. So I actually had to move down my finger more and then grasp and then pull it out. If you look at individual pieces of algorithm, it's not impressive. It's almost dumb. But if you imagine I'm picking on this apple 1,000 times, probably I will succeed 1,000 times without me knowing anything about this individual sequence of decision making. So the point is, stop thinking about what is the optimal trajectory in this small piece of problem. Stop writing paper like that, because that doesn't give us anywhere. Look at our human is doing. We thought as humans are fantastic. We're not nearly optimal. Doesn't matter. We do things good enough because we know how to constitute. We know how to stitch together this algorithm to achieve good enough result. We have absolutely no idea how to write this kind of algorithm using our very quantitative based machine learning or optimization algorithm. Again, going back to the cost function argument, I'm not really sure how we're going to quantify success of picking an apple here. Some might say, oh, I will just do that end to end. Good luck with that. If you don't like something about it, you have to tune it again. And I don't know how you're going to tune it if you do the end to end. You have to collect more data, do another week of experiment, and then you hope, you just cross your finger, your learning abstraction is moving toward what you want to achieve. And think about how many dimensions you have to manipulate when you change your algorithm too. One of the problem I noticed is that our language, our human languages are such a low resolution and then such an abstract. Like if you grab any verb, a lot of verb we're using is such an abstract. I remember one of the researchers, the symbolic, AI person, trying to split and then take it apart. One verb was pour water from one container to another container. He literally take it apart. What do you mean by pour? And then reconstitute what the pour means, and then take it apart in a way that each individual can be translated to computer. And it was such a hard problem. Spread is another terrible words where human has no problem understanding. So I want you to really think about building proper language that we can easily communicate with our computer. We can live without computer in the future. We're gonna have to work with the computer. Another example, clean tray. I asked somebody, clean tray, and quite reasonable people will know what I mean by clean tray. And think about trajectory optimization of this task. Don't try to just solve one piece. You have to do everything together, right? Otherwise, you cannot work. I want to show you a slow motion. Otherwise, you don't know what's going on. This is what's going on in the real time, slow motion. Now you can see maybe a little bit. He's not even grasping anything. See, everything is just sliding. It's almost like a hand is riding ski on an object. Like, everything is sliding, and he's just throwing things. And every tray is he grasps differently. He rotates slightly differently and rubbing things slightly differently. And this is just mind-boggling. How we are what kind of cost function are you gonna write to maximize the efficiency of cleaning? I want you to think about what kind of intelligence going on in their hand, fingers, and force control. Is that trajectory or force? Are those only language we have? We probably need more, right? If you think about intelligent behavior, intelligent algorithm, a lot of people there, I'm pretty sure all of you, your judgment is biased by what humans are good at. If you look at some behavior like making peanut butter jelly, you don't think it's an intelligent behavior. My son can do it. Like picking on a key from your pocket, you don't think it's intelligent behavior. Oh, AlphaGo can play Go and win the Go. Wow, that must be intelligent. Writing equation is intelligent. Those are not things we are actually good at. Humans are not evolved to do this. Humans are evolved to run and throw and eat. We've been only evolved to handle this physical thing only like thousands of years. Yet our judgment is biased because we don't know what's going on in our body, and then we ignore those intelligence. And without that, none of the physical service is going to happen. So I want you to think about how we think about as intelligence, and then what kind of intelligence do we need? Maybe we should understand animal world. I want to have one data point. This is a C. elegans, 300 neuron animals, 1 millimeter worm, has only 6,400 synapses. It's only 300 neuron. Yet after 35 years of research, we still have no idea how this animal swim. It's not just swimming. This animal actually catch prey and eats and have a social behavior. It actually learn and plastically learn and so on. None of that. We just still don't understand how the swimming works. And throwing just a neural network to solve this problem I'm not really sure how that's going to solve everything. Human has a 20 billion in cerebellum cortex, and then about 100 billion in our cerebellum, which is mostly handling balance and motor control. So when it comes to this dynamic, context-rich manipulation, like motor control side, we have a very little idea. And then if you're thinking about robotics, we have to start building these concepts and languages and notions a lot more than things we usually deal with: the position, velocity, force. And it's not enough. Think about in the future, we had to handle a situation where elderly population is exploding. US is relatively okay. If you look at Korea, Japan, and Northern Europe, I think within 20 years, 25 years, I think over 65-year-old people will be 40% of population. And we're going to run out of labor. We're going to literally, society will run out of people who can do simple things. We have to prepare for that. Younger generation will have to handle this. So if you look at this simple situation where, I shouldn't say simple, the person just trying to move from the bed to the wheelchair is not that simple. It's such a big deal for these people who have a motor control issue or the lack of muscle force. It's such a complex issue, and then this is one of the most complex context-rich tasks. You have to balance, you have to gentle in the people, and they have to feel how the person feels and so on. Even that, this person is constantly talking with the person. Think about that. So wrap up quickly. Collision is sometimes unavoidable. Collision is necessary, so we have to deal with that. Don't avoid it. High IMF machines are essential for contact, to manage the contact forces. And new methods, tools, words represent abstract concepts in physical intelligence, not only for the computer, but also for us to, at least we can start communicating each other. Thanks for listening. This is my talks, about 4 hours. So hopefully we have enough time to question, answer, interact. Thank you very much.
Great. Thank you very much, Sangbae. There's a lot of really interesting ideas in there. So we're going to be transitioning to question answer part. I did see that there were a few people with raised hands in the attendees. If you just want to enter your question into the Q&A box at the bottom of Zoom, then we'll see the questions, and then the panelists can ask them for you. So to begin, I just want to introduce the panelists that we have here today. We have Jessica McWilliams. She is a third-year PhD student in my group. And we also have Shane Rosenlevy, who is a second-year PhD student in Dan Kodashek's group. So I'm sure we have a lot of questions for you following that very thought-provoking talk.
Thank you. So I guess I'll start with one of my own questions, sort of to give time for questions to get entered into the chat. So what are your thoughts on the trade-offs between solve time and model complexity for MPC or even the regularized predictive controller?
Fantastic question. I don't know. We look at actually one of the paper from the graduate level and talking about what simplified model is better. Is a big question. I mean, we use one rigid body model, and then assuming there's a thruster at the wrench source at each shoulder, which is eventually kind of simplifying the leg dynamics. That works reasonably because the quadruped shapes look like that. Is it going to work for a humanoid? Because the mass distribution is different. The humanoid legs are much longer, and so you cannot just like oversimplify the cases, because case by case. What if the robot foot has some like tools, and then that get actually heavy? Then our simplified models start working. I think I personally, it's all relative, right? Compared to other researchers, care more about speed than accuracy. Our MPC, convex MPC prediction, and then we compare with our actual result, they are completely different. If you think about why it still works, because it actually pushes in the right direction. not necessarily follow exactly that trajectory. That doesn't really mean much when you're trying to just stay upright. You know, again, the analogy, the situation in the factory, a millimeter accuracy error is a huge deal. You're going to break the product. When it comes to mobile robot moving around your house, a few millimeter off from the trajectory doesn't really mean anything. You rather stay upright and then off by a centimeter on the trajectory. So I think this high level of behavior characteristic is a lot more important than following your model or following your optimized trajectory. So in that sense, I'd rather sacrifice model accuracy and then speed up the solving problem. Because if you solve problem quickly, you can look at far ahead in the future, or you can solve more frequently, so you can adapt quickly. As long as your high-level algorithm characteristic is the right direction. If it's not the right direction, none of this matter.
I'll also ask one of my own questions. So regarding the cost functions, as you mentioned, sometimes we don't really put in the cost function that we actually mean, and you're optimizing this many times in your loops. I'm wondering if you thought about ways of maybe incorporating kind of a lower bandwidth of, or lower frequency of human feedback into the optimization, so that you can, maybe you don't know what the cost function ends up being, but you can be closer to what you actually want.
Yeah, I think that's just a very frank statement. Everybody does it. Even the end-to-end learning people does it. Everyone does it. They just don't mention it in the paper because there's no systematic way to do it. They wouldn't like it. Like I don't know how many optimization or learning can be done once. Just put this cost function. Oh, I love it. Just submit paper. You're writing paper. You can write paper every week then, right? And something you don't like about it. Then why can you quantify that? Can you quantify the things you don't like about? Why you don't like about? It's a lot more difficult than writing a function, right? And as simple as the leg locomotion, I shouldn't say the leg locomotion is simple, but much simpler than manipulation. So, but the stay upright, like stability, the very abstract concept of stability, you can't easily quantify. It's actually very complex. There are many things are up in the air. So I think just inevitable at this point. Leslie Kebling says that she said like, well, I think human has to design it. Human has to design a architecture of algorithm in a way that each box, you have to rely on computers and optimization, but each box is not too big in a way that I call the gray box. There's no white box there. Everything has some aspect about it, but don't have any black box, because if you have a black box, you can't tune it. You have to do complex system, and you need to have a multiple boxes and then make each box reasonably small in a way that you can tune these boxes with the human loop, slow loop, and then you can maybe get somewhere. If you look at real software that actually applied in the real products, they're all like that. If you look at Tesla autopilot, there's a automatic picking robot in the warehouse. They're all humans architecturing and tweaking. Otherwise, it's going to have an accident every minute.
Thanks.
Wow, there's a lot of questions in the chat.
I'll ask a question from the chat.
Sure.
What are the implications of considering friction forces as inertial forces, since friction is not conservative?
That's a great question. But what I'm saying is not that I included inertia in the model. No, I'm saying that effectively, in terms of impact mitigation, when you design a robot, you have to really be careful with the inertia, friction, because that acts as inertia, which means impact it will show. In high impact, the friction will show as inertia. So that's bad. So even though you have a small inertia, if you ignore your friction, the impact mitigation factor you realize in your paper is not going to be same as a real robot. So I'm not saying that you should model that way. It's more like a design guideline.
We have a question from Professor Markiam regarding the patient transfer task, and he wants to know if you're making progress on that. He says he's working on that kind of problem as well.
I just throw that as a like one of the big challenge. I'm glad that you're working on it. I'm so far from it. I'm just working on the component technology that eventually allows to do this. I'm interested to hear your solution. It's always more practical, and then I think this practical solution will be better. I saw some like crane type of people, the technique, but I'm not working on it at this point. I'd love to chat.
So I have a question from Wei Shi Chen. Due to the manufacturability, sometimes it's hard to actually make a machine with low inertia or IMF actuators. What are your thoughts on optimizing the behavior on a badly designed machine that has high inertia?
Optimizing the behavior on the bad design machine. Well, in high dynamic situation, there's only two values you can manipulate. One is acceleration, one is inertia. So either reduce inertia, which is not an option in this case, so you have to reduce the acceleration. One thing you might want to consider is the inertia matrix, again, is a 6th dimension. So when you approach object, you can actually approach in a direction where you have a lowest inertia. Like, you know, that's why we're running on the toe, not in the heel. If you hit in the heel, that's bad. So you can actually look at the inertia or ellipsoid and then look at, oh, this is a low inertia direction. You approach that. That might be a way to go. That's why we have a finger. Finger, you know, even though humans are such a nice IMF, I don't want to deal with anything with my wrist. My finger, your IMF jumps up, your inertia drops significantly because it's serial chain.
So to follow up on that, I guess you showed a lot of different machines also that had very similar designs, but were at different scale, right? You had your Cheetah and you had your mini Cheetah. And I assume that you used different actuators or had some design changes between them. Can you comment a little bit on when you're thinking about different scales, what are the different design criteria that you need to consider?
Fantastic question. I am actually still working on it and don't have a great answer. A few things we're looking at, a few things like the isometric scaling, like mass, the length doubles and mass goes 8 times. And then roughly I'm trying to follow that, like, can I generate 8 times more torque if I double the size? Or if you drop in half, like 8 of it. So I try to capture that. At speed and radians per second, we're trying to keep similar because that's a rotational space. It's independent from length. And the stiffness, we care so much about transmission stiffness from the motor to the limb. That is something we're still struggling. We don't know how stiff is better. We literally spend like a month in choosing a belt. Or not because the belt is hard to choose, actually because the belt companies are terrible at communication. But the stiffness is something we don't quite know. We do rough simulation. What is a resonance frequency of that transmission rotor to the ground, and then try to maximize it, like at least like 30 hertz or 40 hertz. If that belt is too soft, and then basically act as series elastic, and then you lose the force bandwidth. And then as I show you, like 80 millisecond, I can control my ground action force. Same thing as a manipulation. If you have contact time is short, you need to have a high bandwidth system. The stiffness is very important. I don't know how to scale up and down that as well, but we'll see. Maybe we can come up with something and we can write a paper about it. But isometric scaling still works.
So Professor Michael Pozo says, thank you for the great talk. Thinking back to your example of grasping apples from a pile, your human control policy seems reactive, though we could argue about what that word means. Do you think there are models at play here? And if so, what role might they be playing?
So there are many people debate about, like, do we have a physics engine in our brain? And some say no, some say yes. I think we do have some physics engine, probably not similar to what we have in our computer. Because there's a very interesting example. One of my visiting professors working on right now. If you throw an object and then when you catch it, humans surprisingly catch object in the desired location. And if you think about it, like this object is landing in your hand, somehow your hands are not moving down that much. There's a predictive controller to cancel that momentum. And we kind of do it so well. If you look at basketball play, like basketball pass, and then you just throw your hand and stop the ball right there. Does it make sense? Your basketball is a 600 gram and then moving pretty fast, but your hand stopped the ball right there. It's impossible without having predictive anticipatory behavior. So I think we have some sort of physics engine going on in our brain. Otherwise, it's not going to work. As you said, like, what do you mean by reactive? I'm pretty sure we're very reactive, but reactive and this anticipatory part of the algorithm, they are severely competing each other all the time. Sometimes that's why you make a mistake. Your predictive part, try to override reactive part. No, reactive part override, and then that sometimes you fall. This is something we have no idea what's going on. There are people working on research, but their result is very minimal. Tell us very little bit about it. I think, again, we only need to get inspired by. We shouldn't try to copy. I think eventually we need to find a more practical, simpler solution. But those examples really opened our eyes to look at different direction, because sometimes we're stuck in the kind of convention of the legacy of what's been done the last 300 years. We're still using Newtonian mechanics. So think about different way to look at it. So that's where we can get inspiration, by looking at the animals. We shouldn't copy it. I think we can copy it.
So we have a question from an anonymous attendee. You mentioned Unity for simulation. What are you using to run physics under the hood? More specifically, how are you modeling contacts and proprioception in the simulation?
So we use our physics engine, which is a articulated algorithm, body algorithm, which is a Featherstone algorithm. But we include our rotor inertia very carefully, so that it's real. You can actually add reasonably well in like a bullet or a conventional dynamics engine. The URDF doesn't actually have a form. You can actually doesn't allow you to add those inertia, but you can just add a diagonal term only. That's reasonably good enough. But contact dynamics is, I think everybody's doing the same thing. We actually talk about contact dynamics in our class. It's just none of the contact dynamics are accurate. We don't even choose contact dynamics because one is accurate or one is less accurate. We just choose that works without breaking down or slow down significantly. I still remember our first Cheetah one dropping in the space and then landing. That like 3-second simulation took like a 30 minutes, because if you do realistically, it's not realistic to actually use it. The momentum-based canceling force calculation in the velocity space, that's what everybody's using, but that's what we use. Unity is just a visualization. It's nicer.
So we have a couple of questions, one from Andrew Specian and one from an anonymous attendee regarding soft robots. So some people are wondering if there's a mechanical solution to walking on softer surfaces, and like similar, you mentioned the yoga mats, and also if there's ways to exploit the idea of the physical intelligence on soft robots or soft end effectors.
I think we can solve everything with the algorithm and high bandwidth system, because if our robot have a tungsten foot and they're walking on the glass, it's not going to work. We need to rely on some physical, like the embodied intelligence, or like the material itself. Like that's how our fingers are. Like our fingers are such a fantastic. We still have a rely on this like nicely padded part of our finger, and none of these are actually active. These are just passive. But I don't want my entire finger to be compliant and the 1 degree freedom, because I want to actually manipulate this. So the soft robotics idea is good in a way that as long as it doesn't lose your controllability. I don't want to replace like half of my motors with some soft material, because I can't do things I want to do. But interface, you need to have a material that handle impacts, for example. Like a catching ball example, our palm skin does so much of work that we can't really handle with our actuator. So that combination is definitely a way to go. I saw somebody talk about stability and contact force feedback.
Yeah, so I think there's sort of two questions along that idea.
Yeah.
Diego Caprali asked that you mentioned issues and stabilities with force feedback. Can you explain what issues you've seen? And
So,
Yuming
go ahead.
is asking for you to elaborate on Digit's force bandwidth issues.
Digit?
Digit and Cassie?
Digit is actually, well, Cassie, those are actually not quite series elastic. They don't rely on the deflection as force sensing. They're actually using our proprioceptive force control idea. And the springs are very, very stiff. But yet, it's a whole structure has a quite of a compliance. So probably suffer from a little bit of bandwidth. I don't think that's a bad thing. Just the machines are long and that's how it is. Force control feedback is the force sensor feedback. This has been the severely researched in the 90s, actually. The many haptic community has been working on and showing a bunch of instability issue. I can explain it more as physical as possible because most people don't think about it. They look at the equation. They don't look at the actual structure. Every force sensor has a spring. Force sensor is very high stiffness spring. You measure the deflection using strain gauges or piezoelectric. And then imagine you want to shape your inertia. I want to drop my inertia at half, for example. In the equation, everything looks fine. The equation doesn't tell you anything about each component's bandwidth and anything. If you hit it, you're deflecting that force sensor spring, and then that's where the force rise. And then that's how much you're feeling the force. In order to have a force feedback to shape your inertia, you need to react as the force rise. You have to react before force rise, like while the force is rising, you have to accelerate, decelerate in the direction so they can reduce the inertia. We're talking about impact, which is a matter of a kilohertz. Force sensors are typically like kilohertz to 2 kilohertz, depends on how soft the spring is. And then what is your actuation bandwidth? How fast actuator can accelerate? Most robotic arm is about 2 hertz or 1 hertz. DLR arm has a torque sensor every single joint. 6-axis impedance control, all can be done in the force sensor feedback. 6 force sensor or more actually having into the system to have the feedback. That arm can have a force bandwidth of the arm like 2 hertz. So all these demonstrations is under 2-3 hertz. Like 1 hertz. Demonstrations are all 1 hertz. Why do you care acceleration or inertia when you're doing only 1 hertz? You should care when you're moving really, really fast. Our robots are hitting on the ground, having impact of matter of like 100 hertz. So your mismatch between the force sensor bandwidth to the actuation bandwidth, these go doomed to be unstable. So if you push something, you measure 1,000 hertz. Oh, I want it to be 30 Newton. So actuator said, pull back, pull back. Once you pull back, your force goes 0. Oh, no, I want to 30 Newton. Hit, oh, 1,000 Newton. No, pull back, pull back. That's why chattering happened. That's typical instability where your controller bandwidth is not enough to handle your plant bandwidth. In this case, plant is quite complex because it's a hybrid system. But so it's like you're balancing your finger in your a pencil. If a pencil is very, very long, you can balance it very well because system dynamics is slow. If your pencil gets shorter and shorter, you can't balance because my finger-eye coordination loop is too slow that it can't catch up with this fast dynamics. So whenever you write control, you have to think about what is the behavior of your dynamics you're controlling, and then what is control force or control factor, and how fast can I change? This has to be at least like a 10 times, 20 times faster to guarantee the stability, no matter what algorithm you're using. So when you design your robot, when you control our body dynamics, that's about 3 hertz-ish, 2-3 hertz, and then we design the control loop based on that. And then force control, it goes up to 100 hertz. So we need to have a 4 kilohertz control loop, and then our mechanical bandwidth should be at least like 50 hertz. So all these things is actually very important in real life and real dynamic situation. And none of this shown in like any equation you learn from the book. That's the problem.
So I'm wondering, so you've presented this paradigm of the proprioceptive actuation, you presented this IMF, and that generally you want the IMF to be fairly high. And I'm wondering if you think that's always the case and that the trend is going to be to move robots into proprioceptive actuation, or is there a certain environment or task that's not well suited
I think it depends on task because we are still struggling to achieve high band IMF and high payload. That's why manufacturing arms are designed that way, because they want to have a relatively slow. They're not that slow, but they have a high payload. I want to carry heavy things, and if you know to be low inertia, you're doomed to have a low force. That's just how it is, unless somebody reinvent our actuator. And another factor you want to consider. Proprioceptive actuation is fantastic, it's great, high bandwidth, but high bandwidth, low inertia means it's also dangerous. You can accelerate very quickly and then hit somebody. We've been looking at the papers where, joint impedance for safe robot. Safety is nothing to do with the joint impedance. It's all about speed and mass. If your things are moving fast and then heavy, everything is dangerous, no matter what joint stiffness you have. So, safety is one concern and payload is one concern. But when it comes to small force but highly interactive, I think proprioceptive is definitely the way to go. So we're going to see the mix and match, I think. Like hand has to be high AMF. Arm, maybe. It's okay to be low AMF.
So I think the last question I'll ask one of my own. With the increasing availability of off-the-shelf, highly dynamic walking robots from companies like Boston Dynamics, Agility Robotics, Ghost Robotics, what role does academia have in the design of walking robots?
Designing walking robot. I guess like academia's role is presenting something new. So if you have any new idea, you definitely should build your own. Our lab is not necessarily building robot to presenting new idea. We're building robots so that it does what we want. Because the commercial robot cannot do what we want. So that's actually a dilemma. Like we cannot publish a paper on our robot design because nothing is really new. We just design very, very well. And yeah, we're academia, so we cannot even sell it. That's why we're giving out for free. Yeah, that's a good question. Designing a robot is tricky in academia. That's actually something we had to really think about seriously as a community because we're losing all these great designer and mechanical people to industry, and then we're moving the other direction, or academia is living in this mathematics and equation world without realizing what's going on in the real world. Good point.
All right. I'll ask one last question just to close us out. So during your talk, you showed some systems that were very good at reacting, and the intelligence was embedded into the design and the physics of the robot itself. But then at the end, you brought up some situations where tasks are very complicated, or situations where the animal that you were looking at has quite a bit of computation happening. So I wonder, and the title of your talk is Physical Intelligence, right?
Yep.
So I wonder if you could comment on where you think the limits are. Do you think eventually we can embed a lot of intelligence into the physical body? Are there tasks that you can only do with algorithms? What do you foresee as the balance between these two?
Well, so what I mean by physical intelligence is something I don't know. The one that I did so far is providing proper direction to achieve what we want to achieve. It's a hardware side, but I didn't do anything in the physical intelligence side. I'm just trying to make the point that we need to take a look at least, and where the intelligence should be. I don't actually care too much where. A lot of people like, oh, should I be whole distributed? I think I don't care if the one computer in my robot can do everything, as long as it does the proper thing. But I think it's all algorithm from now on. I mean, unless better design definitely will help, like a proprioceptive finger with a very nice pad and high friction surface and robust and so on, nice sensor. But that's more like gradual improvement in my opinion. And then that's a kind of orthogonal to what intelligence you have, which is purely algorithm. I think one thing I reiterate is the good algorithm doesn't mean faster solvers or efficient optimization tool. including machine learning tool, because these are just relying on the quantitative cost functions, and then that's only solve one problem. As you saw, like pick an apple, my hand make a decision 4 or 5 steps reactively, and then the whole thing happened in 0.6 seconds. You can't do that quickly if you're running full dynamics model, full searching for global optimal. None of them matter actually when it comes to this fast dynamics. So you need to have an algorithm that have a common sense and then understand the abstract concept. I'm just saying it, and I'm not saying this is easy. This is a grand challenge in robotics, in my opinion. So first thing I think we should take a look at is like, how would you communicate abstract concept with the computer? Machine learning, the neural network does it their own way. That's how they recognize things. But that abstraction is something we don't quite understand. It's very different from how we abstract things. So how can we close the gap between machine learning abstraction to human abstraction, or how to even translate that? That's probably the next thing to do.
All right, great. Well, thank you, Professor Sangbae Kim, for this very interesting talk and the stimulating discussion afterwards. I believe Gabby has some things to announce.
Yeah, well, thank you, Cindy. Thank you, Sangbae and panelists. And thank you all for joining us here today. Please tune in next week on Monday, October 12 at 2:30 Eastern Standard Time to welcome our next speaker, Dr. Lynn Parker from the White House Office of Science and Technology Policy. For more information on upcoming events, be sure to follow us on social media and check our website. Thank you again and have a wonderful day.